Okay, I just wanted to give a little mini lecture on intermolecular forces. This is a topic that fits into a number of chapters that we teach. It fits into actually chapter 1, where we just talk about bonding and polarity and dipoles. It fits into chapter 7, where we talk about solutions. It fits into chapter 9, where we talk about gases. So there's not really any super convenient place to insert it into our lecture schedule. So I thought I'd do a little supplemental lecture on it. So intermolecular forces. What are intermolecular forces? Intermolecular forces are, as you might guess from the name, interactions that occur between molecules. So forces of attraction, they could also be forces of repulsion, but since repulsion simply pushes away the molecules, they're not usually long-term effects. So we usually think about them as in terms of being favorable interactions, but interactions or attractions that occur between molecules. I've got 7 or 8 listed here, depending on how you categorize them or how you organize them. And I've wanted to go through them in terms of their strength. Strongest intermolecular forces to weakest intermolecular forces. So we'll start with first the ion-ion interaction. Now, these types of interactions are often omitted from a discussion of intermolecular forces because they're very similar to ionic interactions that you get in an ionic bond. So I want to make a distinction here. It's a very technical distinction. That an ion-ion intermolecular force is an intermolecular force between ions of different molecules. Okay. Not to be confused with ionic bonds, which are interactions between ions in the same molecule, or an interaction that holds 2 ions together in a molecule to form a molecule. So I've got a little drawing here. We've got sodium chloride, Na plus and Cl minus, and each sodium is ionically bonded to a chloride. So we've got an ionic bond between an Na plus and a Cl minus, and then another ionic bond between another Na plus and Cl minus, and then a third ionic bond between a third Na plus and a third Cl minus. But those molecules are still attracted to each other. Even though the chloride in the first molecule is bonded to the sodium, it can also interact with the sodium in the second molecule. Now, that wouldn't be considered an ionic bond because chloride would only make one ionic bond with a minus charge would make one ionic bond with a plus charge, but it still feels the neighboring positive charge. So this is an intermolecular force. It's a force of attraction between different molecules, and the groups or the kind of entities that are involved in that interaction are ions. So it's an ion interacting with an ion on different molecules. Now, these happen all over the place, not only in solids. Of course, they might occur in a salt like this, where you've got a crystal of these, say, NaCl molecules all stacked very nicely onto each other. You're going to get lots of these ion-ion interactions. But you can also get them in proteins. Amino acid backbones and side chains often occur ions, or often involve ions, and those ions can interact with each other. Sometimes you might call them salt bridges in those contexts. You can imagine all kinds of situations. Anytime you have 2 ions, either in a solid state or in solution, that can interact with each other, we're going to call it an ion-ion interaction. Okay, and it's the strongest type because these are full charges. We're going to see most of the other types of interactions that we see involve partial charges, or at least one of the participating entities it has a partial charge. But this is 2 full charges, a full plus and a full minus. Now you could get even stronger if you had, say, a positive 2 ion and a negative 2 ion, right? Those would be really strong interactions. like calcium and oxygen, calcium and oxide. So these can be very strong depending on the relative charges of the ions. But everything else that we're going to be looking at involves partial charges, so they're going to be weaker than this. So the second type is an ion dipole interaction. This is the second strongest type of intermolecular force, and it occurs between an ion, which we said again is a full charge, but then the other participating entity is a dipole moment, okay, a partial charge. So a dipole moment overall for a polar molecule, or even a polar bond, the positive or negative end of a polar bond. Okay. For example, when you dissolve salt, say sodium chloride, in water, the ions separate. And I've drawn a little picture of this here, where the ions of sodium and chloride have become separated, and instead of their charges being satisfied by each other, they are satisfied by the water instead. Water, as you hopefully know, is polar. The OH bonds are very polarized, so the oxygen in water has a very high negative partial charge, and the hydrogens on water have a very high positive partial charge. So you can see the way that these water molecules will arrange themselves around these ions. The oxygens will orient themselves around the positive sodium ions, and the hydrogens will orient themselves around the negative chloride ions. So this is an interaction, an intermolecular force between the positive, let's say the positive end of a dipole, and a negative ion, an anion, and or the negative end of a dipole, say the oxygen, with a positive ion, a cation. Okay, so those are ion dipole interactions. And again, they're strong because they involve a full charge. Those ions provide a lot of attractive electrostatic interaction. But it's weaker than the ion-ion bond or intermolecular. It's weaker than the ion-ion intermolecular force because it's a partial charge, not a full charge. Okay, third type. This is the type that we're going to break into two different kind of subcategories, is the dipole-dipole interaction. So this is an interaction, an attractive force between dipoles on different molecules. And again, these are weaker than the ion dipole because now we're only dealing with partial charges. There are no full charges in a dipole-dipole interaction. So I've got a picture here of two what are called ketones. The ketone is a C double bond O, where the carbon has other carbons on it. So you see the carbon has two CH3 groups and the double bond O. That makes it a ketone. Now the ketone is a polar group because the C double bond O is a polar bond. Oxygen is more electronegative than carbon, so it draws the density in that double bond towards the oxygen, leaving the carbon a little bit electron poor and the oxygen a little bit electron rich. So you'll have a dipole there, the negative end on the O, the positive end on the C. And if you bring two molecules like this together, you can get an interaction between those dipoles, where the negative end of one dipole interacts with the positive end of another dipole, and the positive end of one interacts with the negative end of another. They can be the same molecules, like in this case with these two ketone groups, or they could be different molecules. You could have an interaction between a dipole on a ketone like this and the dipole on water. That would also be a dipole-dipole interaction. So they don't have to be the same. They don't have to be even the same magnitude. Their dipoles can be large on one molecule and small on the other molecule. But there does have to be partial charge originating from these kind of asymmetric electron distributions in a molecule. So that's the dipole-dipole interaction. Now there's a special type of dipole-dipole interaction, which is called hydrogen bonding. And you see that I put bonding in quotation marks here because this is not a real bond. It's not a covalent bond. It's not an ionic bond, but it's it's an intermolecular force, but it's a very strong intermolecular force. It's so strong that it at one point was apparently considered to be a bond. So this is still a dipole-dipole interaction, but it's a special type of dipole-dipole interaction because it involves interactions between the largest types of dipoles that you can get. Okay, the illustration I have here is HF. Hydrogen is among the least electronegative, or in fact, I should say it is the least electronegative atom that participates in covalent bonding. Fluorine is the most electronegative atom that participates in covalent bonding. So pretty much the most polar bond, the most polar covalent bond that you're ever going to get is an HF covalent bond. The atom that wants electrons the least bonded to the atom that wants the electrons the most. Okay, so if you have a dipole-dipole interaction between two HF molecules, that's going to be pretty much the strongest type of dipole-dipole interaction, and we call that a hydrogen bond. So there are three situations where we get hydrogen bonding, that is to say, a dipole-dipole interaction that is really unusually strong. So that's with H bonded to F. You can also have it with H bonded to N or H bonded to O. Okay, so a polarized H, an H that's been very polarized because it's bonded to an F, because it's bonded to an N, or because it's bonded to an O, will participate in dipole-dipole interactions that are very strong, and we call them hydrogen bonding. So water does this. Okay, I've got a picture of two water molecules interacting here. As we said, an OH dipole is very strong. So the positive end of the water, the H end, will interact very strongly with the O end of another water molecule. Right? So that's the dipole interaction between an OH and another OH. So that's a hydrogen bond. Hydrogen bonding is really important in a lot of situations, almost too many to even try to count, or too many to even try to illustrate. But a couple ideas. Water has a very high boiling point. What makes a substance boil, when a substance is boiled, what's happening is the heat, the thermal energy, is disrupting intermolecular forces between molecules. And that's why the liquid molecules are kind of separated from each other and they become a gas, where the particles are flying freely and not interacting with each other anymore. The fact that water has a high boiling point is a testament to how strong hydrogen bonding is. It takes a lot of heat, a lot of thermal energy to cause, let's say a liter of water to have all of its hydrogen bonds disrupted. Okay. That's one example. Okay. High boiling points often result from strong intermolecular forces like ion-dipole interactions, ion-ion interactions, or hydrogen bonding. Another thing is the backbone of, or I should say, the two strands in double-stranded DNA. Okay, the double helix of DNA. Those two strands are actually held together, held to one another by hydrogen bonding. It is hydrogen bonding between the backbone of one strand of DNA, or one single strand of DNA, and hydrogen bonding with the backbone of the other single strand of DNA that gives DNA the double helix. And the fact that our DNA doesn't just fall apart is testament to how strong these intermolecular forces are. Like I said, almost too many ways to try to count, to try to come up with examples for. But virtually everywhere you look, in nature, in chemical reactions, in origins of physical properties, almost always come down to intermolecular forces. And because hydrogen bonding is so strong, it also turns out to be very prevalent. Okay, so continuing on, we're getting weaker here. Okay, weaker types of intermolecular forces. The fourth, or again, maybe if you want to think of it as the fifth type, if you want to think about hydrogen bonding as being different than a dipole-dipole interaction, that's fine. But our fourth type is an induced dipole interaction. Okay, so as this might suggest, as opposed to a dipole being permanent, as in the case of what say is on water, okay, the bond dipole on water is permanent. Oxygen is always more electronegative, hydrogen is always less electronegative, and so there will always be an asymmetry in charge in that dipole. Okay, but an induced dipole is a little bit different. There are some molecules that are nonpolar. They have nonpolar bonds, but they can be induced into a polar state. Okay, and so usually these are molecules that have big, squishy is the term I like to use, electron shells. Like, for example, bromine, Br2. These are two large atoms covalently bonded to each other, have equal electronegativities. Of course, they're both bromine. Of course, they have the same electronegativity. So there's no inherent asymmetry in these orbitals. And there's lots of electrons in them. They're large orbitals filled with lots of electrons. And so think of it as like a bathtub full of water. And the water can be sloshed onto one side of the bathtub and it will slosh back to the other side. Just left on its own, the water will eventually even out and there will be an equal distribution of water throughout that bathtub. But you can induce an asymmetry in that. So, for example, with bromine, okay, we've got our picture of bromine on the left, a nice, big, squishy, non-polar molecule. And then we bring into proximity of it, let's say a cation. Okay, we bring a cation near the bromine molecule. What's going to happen to the electron distribution around bromine? All of the electron distribution is going to be drawn towards, or not all of it, but a lot of that electron distribution is going to be drawn towards the cation. So you're going to get a polarized bromine molecule where one end has more electron rich, more electron density, more electron rich, and the other end has less electron density, is less electron rich. So now we have a dipole, but it's not a permanent one, right? Because as soon as that positive charge floats away, drifts away in solution, that dipole is going to go away. So it's an induced dipole. It's a temporary dipole. As a result of being temporary, it's much weaker. Okay, it doesn't take a lot for that potential for intermolecular forces to go away. So we can get an induced dipole that induces other dipoles. So a polarized bromine might have another neighbor that's a bromine, and that molecule might polarize its neighbor, and that molecule might polarize its neighbor, and they'll interact as a result of that. So as you see here, we've got three polarized bromine molecules all interacting. It's like a dipole-dipole interaction. I mean, it's inherently it's the same thing as a dipole-dipole interaction. Okay, it's just that the dipole is temporary, and therefore it's weak, short-lived. Okay, this is why, by the way, bromine is a liquid compared to, say, chlorine, which is a gas. Fluorine, chlorine, bromine, and iodine, the four halogens, the four common halogens, are very similar in terms of their kind of fundamental chemical makeup, but they have very different properties. For one, fluorine and chlorine are both gases. Bromine is a liquid and iodine is a solid even. So the reason why bromine is a liquid, but chlorine is not, is because bromine being bigger has a more polarizable electron shell. And so its molecules can interact by virtue of these minuscule induced dipoles and create a liquid. Now, the liquid bromine actually has a significant vapor pressure. It does not take a lot for a bromine molecule in the liquid state to liberate itself from its neighbor and their interactions and become a gas. Very easy for bromine to do that. Again, it's a testament to how weak these intermolecular forces are, but the fact is that they are there. Otherwise, bromine wouldn't be a liquid. And iodine, it's even more extreme. When you couple a larger, the idea of having a larger molecule like iodine, more electrons, bigger electron shell, more polarizable, also higher molecular weight. Molecules require more kinetic energy or more thermal energy to increase their kind of kinetic movement. Iodine becomes a solid. The molecules are so immobile because of their size and their interactions that iodine becomes a solid. So this is a classic illustration of this. Okay, and then I have a last note that polarizable molecules like bromine can even acquire these temporary dipoles by random chance. There doesn't have to be, like, let's say, a cation in solution like I drew before. Certainly that would do it, but just the random movement of electrons in bromine shell, at one instant you might have a little bit of a dipole. A little bit of one side with more electron density, one side with a little bit of less electron density. And even that temporary dipole can induce dipoles on the neighbor. Okay. So it can be induced by, like I said, a charge, a permanent charge like a dipole or a cation or an anion, but also by just random movement of electrons. And that concept brings us to the last type that I have here, which are called London dispersion forces. Sometimes they're just called London forces. Sometimes they're just called dispersion forces. I will call them London dispersion forces. They're also called van der Waals forces. They can also be called Lennard-Jones interactions. There's all kinds of different ways that these things have been referenced in, let's say, the last 100 years of chemistry. But this is related to the same idea of the random movement of electrons in a molecule that we said could potentially generate a temporary dipole in a polarizable molecule. But London dispersion forces happen even in molecules that are not really polarizable. So these are the weakest type of intermolecular forces, similar to induced dipoles, but are much weaker. Really, they are only noticeable in large molecules where their cumulative effects can be detected or can be observed. Okay, for example, octane. I've drawn octane here. It's C8H18. It's a chain of carbons where every carbon has as many hydrogens on it as it needs to get 4 bonds. Now, all of these bonds are essentially nonpolar. A carbon-hydrogen bond is nonpolar, kind of at the limit. Carbon is minusculely more electronegative than hydrogen, so it tends to drag electrons toward it a little bit more, but it's a very, very, very small difference. Carbon bonds are, of course, completely nonpolar because carbon cannot be more electronegative than its neighbor carbon. So overall, octane is a very nonpolar molecule. However, just because this molecule ends up being kind of like a big blob of electron density, I'm just going to illustrate that. There is no asymmetry in the electrons. It's a symmetrical molecule, kind of no matter how you look at it. And so we end up with just this big blob of electron density. And movement of electrons within that blob can cause tiny, 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 tiny little dipoles. And when you bring two molecules together that can do that, those tiny, tiny, tiny little dipoles can add up. Right here I brought 6 octanes together. And you can imagine that with this giant pool of electron density, you're going to get some favorable interactions. Okay. And those are London dispersion forces. They are significant in their number. Okay, it's not the individual strength of the interaction that matters. It's the fact that they can happen a lot in large molecules. That's why nonpolar molecules still interact fairly strongly with other nonpolar molecules. You don't have to have polarity at all, really, to generate intermolecular forces. You can get strong intermolecular forces without those permanent dipoles. So nonpolar molecules interacting strongly with nonpolar molecules results from these fairly large molecules with very minuscule dipoles, but those dipoles interact in large quantities. Okay, so you get lots of interactions from these. So that's it. That is the list of the most common types of intermolecular forces. I guess we have 6 if you want to think about hydrogen bonding as being a separate type. Just to review, we had ion-ion, okay, the strongest type between 2 full charges, full +1 and a full -1. Not to be confused with an ionic bond, but an interaction between different ionic molecules or different molecules with ions on them. Second was the ion dipole. Now we have a full charge in the ion and a partial charge in the dipole. For example, salt interacting with water in the aqueous state. By the way, I didn't mention, I've got it written here, but this is why the boiling point of water increases when you add salt to it, right? When you cook, say, pasta, you're supposed to put salt in the water. It not only adds flavor, but it lets the water get hotter before it boils. By adding salt to water, you increase the boiling point. And a part of that is because you are now allowing ion dipole interactions to occur. Without the salt, pure water would only undergo hydrogen bonding, dipole-dipole interactions. But adding salt to it, you get stronger intermolecular forces. It requires more energy to disrupt them, and so your boiling point is higher. So it's the ion dipole. Third, we had the dipole-dipole interactions, which were partial charges interacting, and we could have normal dipole-dipole interactions between average strength dipoles. But when we have particularly strong dipoles, that is to say between HN, HO, or HF, then we get what we call hydrogen bonding. These are just exceptionally strong dipole-dipole interactions. Fourth, we had induced dipoles, where we had a non-polar molecule that was polarizable, that could be given a temporary dipole by virtue of some external charge influence. For example, bringing a cation or an anion near that molecule could induce a dipole, and then those induced dipoles could interact with others. You could have a dipole that induces another dipole, which induces another dipole, and then those can interact. And lastly, the London dispersion forces, also known as van der Waals or Leonard-Jones interactions. All right, that is it. Hopefully, This was interesting. I promise you that we will use them more going forward. They might not seem super important in terms of general chemistry. You learn about solutions. You can have types of interactions in solutions. You can learn about gases, which have minimal types of interactions. But I promise you, when you get into higher levels of chemistry, organic, for example, these ideas become very, very important. So there you go. I hope they serve you well. Let me know if you have any questions.